Have you ever just looked at something and wondered, how does that not break? Well, today we're diving deep into the hidden science of what I like to call supersurfaces. We're talking about the secret, microscopic engineering that makes the world around us unbelievably tough and built to last.
Right? I mean, how exactly does a jet engine handle that insane heat? Or how does your phone screen, hopefully, survive yet another drop? You might think the answer is always some brand new miracle material, but often it's more like a detective story, an investigation that's happening at the atomic level.
And this is our crime scene. You see, even the strongest materials out there, we're talking top-of-the-line steel, titanium, you name it, they're all hiding a secret. They are covered in tiny microscopic flaws, little imperfections that are basically just waiting for the right moment to grow into a massive failure, like a crack, or rust, or just crippling wear and tear.
And that's the thing you've got to get. The surface of any material is its front line, its first defense. It's a constant, non-stop battlefield against everything the world throws at it. And because of that, it's where most things start to go wrong, which makes it the single most critical and often the weakest part of any object.
So how in the world do you solve a crime you can't even see? Well, you call in the specialists, of course. These are the material scientists, our detectives, and they have an absolutely incredible toolkit they use to investigate these microscopic crime scenes to figure out exactly what's failing.
First up in their kit is the Scanning Electron Microscope, or SEM for short. The easiest way to think about this is as a ridiculously powerful magnifying glass. But instead of light, it uses a beam of electrons to let you see things thousands of times smaller than a single human hair. This is how our detectives spot the first clues. Those tiny little cracks and pores where the failure is just beginning. And then there's this tool, X-ray Diffraction, or XRD. Okay, so if the SEM is the magnifying glass, the XRD is the fingerprinting kit. This is wild. It doesn't just look at the surface, it actually identifies the atomic structure of the culprit. You see, every single material has a unique crystal fingerprint. And XRD is how we check if we're dealing with the right stuff or some kind of cheap imposter.
All right, so our detectives have these incredible tools at their disposal. Now the real investigation begins. What are they actually looking for? What are those telltale microscopic clues that scream a material is on the verge of failing?
Because down at this level, every little imperfection tells a story. A tiny pit could be the first chapter in a long story about corrosion. A microscopic crack could be the foreshadowing of a catastrophic break. The whole point is to read these stories and give them a better ending before things get tragic.
And here they are. These are the smoking guns. You've got your obvious ones, like tiny cracks and pores. Those are just open doors for damage. Then you have incorrect crystal phases. That's like finding the wrong fingerprint at the crime scene. It means the material's atoms are all jumbled up. Flawed coatings or chemical impurities? That's just evidence of a sloppy job. And then you have these very specific bad guys, like something called retained austenite in steel. It's basically a soft, weak structure that didn't form correctly during manufacturing, and it just sits there like a built-in weak point. Okay, so the detectives have found the flaw. Case closed? Nope. Now what? You don't just scrap the whole thing. This is where the real magic happens. This is where scientists can actually engineer a fix, not by changing the entire object, but by completely transforming its surface. And there are a few main ways they do this. First, you can just spray on a shield. Add a totally new super protective coating using something like an atmospheric plasma spray. Or you can bake it tough. This involves using special gases in a process called plasma nitriding to make the existing surface way harder. And a third way? You just zap it with energy, using powerful electron beams or lasers to literally melt and smooth out all those pesky flaws. This quote just nails it perfectly. You're not just patching a hole here. The whole point is to create a brand new surface that is fundamentally different and way, way better than the original stuff underneath it. It's a complete transformation.
So, the fix is in. The surface has been totally re-engineered. But the job's not over, not by a long shot. Now comes the moment of truth, the verdict. That material has to go through a whole series of brutal tests to prove that its new surface really is a supersurface.
So how do you prove it? Well, first, you test its hardness. And I mean literally. They take a tiny, sharp diamond point and press it into the surface to see how much of a fight it puts up. Then there's the wear test. They basically simulate a lifetime of friction by rubbing another material against it for hours and hours. And finally, the corrosion test. They just dunk it in a nasty salt bath to see if it can fight off rust.
And the results? They're almost always staggering. You take a material that was soft, easy to scratch, and prone to failure, and you turn it into something that is super hard, incredibly resilient, and resistant to corrosion. The proof is right there. The fix worked.
So why does any of this matter to you? Because this invisible science is, and I mean this literally, everywhere. It's in the medical implants that have to last a lifetime inside a human body. It's in the aerospace parts keeping us safe at 30,000 feet. This science saves lives, it saves money, it prevents waste. It kind of makes our modern world possible. Which leaves us with a really fascinating question to chew on. You know, we're always hunting for the next big wonder material. But what if the next great leap forward isn't some brand new discovery? What if it's just figuring out how to perfect the surfaces of the materials we already have, unlocking their true potential by mastering this hidden world? Definitely something to think about.